Gr9's welcome. This is lesson 3, video 2. So in the last video I asked you to please do investigation 2 using the FET circuit simulator. So I'm going to do that with you. First I'm going to do the series circuit and then I'm going to do this parallel one. Okay, remember I said we must use potential difference for the cells as being 1.5 volts and the resistances of each bulb must be 1 ohm. Okay, so here's my FET circuit. Let's put in a cell. I need to change it around, so if I want to do that you can tap on the button where the cell has got arrows going around it, or you can even just drag it around if you need to. I'm going to have the positive side, the brownie gold side, I'm going to put on the left because in my circuit that's the orientation that it's in. If you have a look over here, this is the positive side, that's the negative side. Okay, so we've got a cell and then we need to have 2 light bulbs joined with conducting wire. Alright, let's set the resistance not to 10 ohms, I said it must be 1 ohm. And for that bulb, notice how if the resistance on this bulb is 10 ohms and the resistance on this bulb is 1 ohm, the bulb with higher resistance uses more potential energy and so it's brighter. Let's make that be 1 ohm as well. And the potential difference for our cell, I want you to please make 1.5 volts. In the lab, if you're actually using the actual Duracell batteries that you should remember using from last year, those are 1.5 volt cells. Alright, let's put in the ammeter. So if I put the negative side onto the positive terminal of the battery, I should get a negative reading on the ammeter. Notice how the ammeter reading is 1.5 volts with a minus sign in front because I've connected it incorrectly. I need to connect the negative side of the ammeter to the negative terminal of the cell and the positive side of the ammeter to the positive terminal of the cell. So I get a reading of 1.5 volts and that's going to be in the position for voltmeter 1. So voltmeter 1, 1.5 volts. Now let's see what it's going to be for voltmeter 2 and 3. Voltmeter 2. Again, notice how I'm connecting the positive lead, the red lead of the voltmeter, to the terminal of the light bulb that's connected to the positive terminal of the cell. And the negative terminal of the light bulb, I use the black lead there because that's ultimately connected to the negative terminal of the cell. Okay, 0.75 volts, and let's do the same for the other bulb. Also 0.75 volts. 0.75 volts, 0.75 volts. What do you notice if you add up voltmeter 2 and voltmeter 3? So 0.75 plus 0.75 gives us 1.5 volts. So what I'm actually saying is if I connected a 4th voltmeter across both bulbs, I would get the reading of that one plus that one, voltmeter 2 and 3 combined. So if you want to add that to your notes, you're welcome to, you don't have to. Voltmeter 4 would be 1.5 volts. Okay. And I want you to realize that if I connected it like this, I get 1.5 volts on the voltmeter. If I move the leads over there, I'm still getting 1.5. And I can actually move these leads all the way around my circuit. And unless I cross over any component, I'm still going to get a potential difference of 1.5 volts. So let's check that again. Each bulb uses 0.75 volts of the energy, 0.75, but if I connect the voltmeter leads across both bulbs together, I get 1.5 volts, and whenever I connect it, as long as I don't cross over any other components, I'm still going to get 1.5 volts. Okay, so please make a note of that. Now let's do the parallel circuit. So I've got a 1.5 volt cell, 1 ohm bulb connected in parallel, and I need to connect a voltmeter across the cell, across the top bulb and across the bottom bulb. So let's do that. So we've got a cell, the left hand side is the positive side, so swing it around to do that. Some conducting wire. Make sure it joins up, otherwise it won't work. Okay, let's put in our bulbs. Remember to make the potential difference of the bulbs each be 1 ohm. And the potential difference of the cell must be 1.5 volts. Notice how even though I haven't put in the second bulb yet, the first bulb, the top bulb, is already working, and the reason why is because it's connected in parallel. So there's already a closed path for current to flow. So even though the bottom bulb I haven't even added, when I do, it's going to have a potential difference, it's going to have a resistance of 1 ohm. Even though I haven't added it, the top bulb is already working. So let's add in the second bulb. Okay, 1 ohm, and 1.5 volts. There is a button over here called values. If you put a tick in that box, it will give you the values of all your components in the circuit. Alright, time for the voltmeter. Remember, positive terminal of the voltmeter to the positive terminal of the cell, and the potential difference is 1.5 volts. So for voltmeter 1, that's this one, 1.5 volts. Before I even put the voltmeter on in the position of voltmeter 2, I want you to realize that if I move these leads to that position by the bulb, have I crossed over any other component? And you should realize that I haven't. I can go from this bulb back to the cell without crossing over any other light bulbs or resistors. And because of that, you would expect to get exactly the same potential difference, and I do, 1.5 volts. Even if I put the leads over there, 1.5 volts. Can I get from the position that they're in now to the bottom bulb without crossing over any component? Let's have a look and see. Answer is yes, I can. So again, 1.5 volts. I could even put them over there and it's 1.5. Could put them over there and it's 1.5. I could move the leads to be in those positions, 1.5. As long as you're not crossing over any other component, wherever you test the potential difference along that length of conducting wire, you'll still get the same value of 1.5 volts. So 1.5 volts, 1.5 volts. I'd like you to pause the video, and while it's paused, you need to do a conclusion for this experiment. Suggest you do it in pencil so that you can change it if you want to. If you're not really actually going to do it and you're going to cheat a bit, then please at least pause the video and think of what your conclusion should be for this information. So you should have realized that the potential difference, or I'm just going to abbreviate it as PD, please don't do that in tests and exams, is split or divided across components in series. What I mean by that is that the voltmeter reading for voltmeter 2 of 0.75 plus the voltmeter reading for voltmeter 3 of 0.75 gives us, if you add up those two values, you should notice that you actually get the potential difference of the cell. Okay, so that's what I mean that it's divided. Some of that blue goes to the green, some of the energy, the potential difference from that cell goes to the yellow bulb. Some goes to the green bulb, some goes to the yellow, but if you add up the two together, you get 1.5 volts. So that's what I mean that the potential difference is split or divided. All right, let's talk about the parallel circuit. You should have noticed that the potential difference of one component in the parallel circuit is equal to the potential difference of the whole parallel circuit. So the potential difference of one component in parallel circuit is equal to, if you want to abbreviate that just as an equal sign, you can, but don't do that in tests and exams. The potential difference, don't abbreviate in tests and exams, of the whole circuit. What I mean by that is, can I get from this voltmeter 3, can I get from there, I'll do the blue as negative and the red as positive. Can I get from voltmeter 2 to voltmeter 3 without crossing over any other component? And you've just seen, yes, indeed you can. It's the same piece of conducting wire. Can I get from voltmeter 2 to voltmeter 1? Let's have a look. Yes. And on the other side, yes. So that's why 3 is equal to 2 and 2 is equal to 1, so they're all actually equal to each other because they're all connected to the same piece of conducting wire. So that's why potential difference of one component in the parallel circuit is equal to or the same. If you wanted to, over here, if you wanted to say the same as the potential difference of the whole circuit. All right, so there's a relationship between potential difference, work, and charge. There's a formula that you're going to have. The formula is W equals VQ. So W is work done. Work done is measured in joules. V is potential difference. Potential difference is measured in volts, capital V. And Q is charge. Charge is measured in coulombs, capital C. Okay. If you want to rearrange that into a magic triangle, which isn't really magical, you can have W at the top, V and Q on the bottom. So if I cover W, W is equal to V times Q, which is what you've got over there. If I covered V, V is equal to W divided by Q. W, this line means divided by, have a little divide sign if you want, divided by Q. V is equal to W over Q, and if you covered Q, Q would equal then to W divided by V. So you could say Q is equal to W over V. You will be given that formula in tests and exams, but you won't. You need to know how to use that formula. Okay. So let's go through some examples of how to use this equation. So if you've got 30,000 joules of energy, and that's needed to move 0,000006, capital M stands for mega, which is one, you're going to go 10 to the power of positive 6. Mega coulombs of charge through a cell. Calculate the potential difference across the cell. Okay, so let's write down the information that we've got. The work done is 30. How many zeros have we got? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I can write 30 times 10 to the power of 9. Okay. Grade 9s, there is a mistake in your book. I'm really sorry. Please can you fix this? The question was meant to have not been 30 billion joules. It should have been picojoules. PJ, baby P, capital J. And pico is times 10 to the minus 9, if you recall from your SI units. So what we've actually got is 30, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've got 9 zeros, 30, and then 9 zeros. And pico means times 10 to the minus 9 times 10 to the minus 9 joules. Okay, and if on your calculator you go 30 and then you have 9 zeros, and then you press equals, then you take your answer and you go times 10 to the minus 9 using the exponent button on the bottom of your calculator, times 10 to the minus 9, you will see that what that actually means is just 30 joules. Okay, so this whole big expression, all that means is just 30 joules. That's just 30 joules. Okay, so our work is 30 joules. Let's look at the charge. The charge is 0,00006 megacoulombs. So we've got 0,00006, and I told you mega means times 10 to the 6 coulombs. On your calculator, you're going to press exactly that, 0,00006, and then you're going to use the times 10 to the button on the bottom, and then 6, and your calculator should tell you that that is, let's just get rid of that. All that means is that your charge is 6 coulombs. Okay, now we can use these values in our formula. So work is equal to V times Q. That comes from at the top there. Our work done is 30 joules. V is what we're trying to calculate. It said calculate the potential difference. And our charge is 6 coulombs. I'm going to put that in brackets. And our charge is 6 coulombs. If you solve for V, you're going to get 30 divided by 6 equals V, and 30 divided by 6 is 5. So our potential difference is 5 volts. I would like you to please do 2, 3, and 4 on your own. And once you've done that, you can then watch the next video.